Caroline Zer, and this is my lab 4 for Physics 2211. The purpose of this lab was to observe and analyze the motion of a mass swinging in an arc while oscillating on a spring. The key physics concept that we used was the energy principle, and the results were that the x position versus time of the model is very similar to the experimental results that we observed. Again, the key physics concept that we used in this lab was the energy principle, which states that the change in energy of the system equals work done by the surroundings. In this lab, we observed kinetic energy of the mass, potential energy of a spring, and gravitational energy acting on the mass. So we get delta E equals delta K plus delta US plus delta UG. We also use Newton's second law with the velocity update formula and the position update formula to observe the object's velocity and position after certain amounts of time. Here's my tracker analysis. And my system was the mass, the spring, and gravity, and I had nothing in my surroundings, which is why we could set delta E equal to 0. And for my initial conditions, the initial position was negative 0.09203, comma 0.712, comma 0 meters, and the initial velocity was 0. And then those are my graphs in the center from the experiment. For my calculations, the oscillation period is 2 pi times the square root of mass divided by the spring constant. So to solve for the spring constant, I first took 3 oscillations from the graphs that I got from my experiment and took the average. So the average period of oscillation that I got was 1.46 seconds. And then I plugged that into my equation to solve for a spring constant of 7.442 newtons per meter. And then I also solved for the original length of my spring with the net force in the y direction, which equals 0, being equal to the spring force plus the force of gravity. And I used the constants that I knew to solve for my original length. Here's my code. The ball mass is 0.402, and then I put in my position velocity vectors. I also put in the gravitational constant, the spring constant, and the relaxed length of my spring. And then I also put in the equations for updating the spring position and also for calculating the different types of energies that we used. And then continued, at first I defined my initial energies, and then I defined the force of gravity, the force of spring, and the net force. I put in the position and velocity update formulas, and again, the changes in energy are at the bottom. Here are the models that I got. On the left is the energy model where it's change in energy versus time. And then on the right is my x position versus time and y position versus time. And on the bottom is just a picture of my spring and mass oscillating. The results, the spring potential energy, which was in green, and the gravitational potential energy in red oscillate opposite to each other. The kinetic energy oscillates in a different direction from both potential energies, and this is because kinetic energy is opposite to both potential energies, and E total equals kinetic energy plus potential energy. And then for the position versus time graphs, the position versus time model for the x direction was similar to the observed results, whereas for the y direction, it was not accurate as compared to our experiment. Again, we can see the x position versus time, the green or the red and blue lines are very similar, but they're not in the y graph. And then sources of error that could account for these differences are not accounting for other possible energies or forces, such as thermal energy and drag force. And then just an inexact tracker analysis when clicking on the point mass at each time step. Then for my what ifs, for the model system, is the energy principle satisfied? I said yes. Looking at the energy versus time graphs, we see that the sum of the kinetic energy, gravitational potential energy, and spring potential energy is the total energy, which is 0. And we see that all 3 changes in energy kind of opposite each other, which allows them to equal 0 for the total energy. And then make 2 estimates of the period, one using the x position data and one using the y position data. So this can be found by looking at the time of the first 3 oscillations and then taking the average. So for the x, again, I said 3t equals 4.318 seconds, and so t equals 1.46. For the y, I said that 3t is 4.476 seconds and t is 1.492 seconds. So there is a slight difference, and the difference in the period would affect our calculation of the spring force constant. That difference would result in different forces, or this difference may be a result of different forces or energies that we did not account for in this lab. Thank you for listening.